Hello, you theory of probability luminaries. I decided to use a different medium for filming. I think Zoom maybe has some more features. It doesn't seem to be quite as glitchy. Uh, so I'm gonna give this a shot. Okay. I said last time that I wanted to go through that example on the Pareto distribution. So this is where I'm going to do that. But before we do that, I wanted to look at something here. So let me share this screen. Okay. So here's a really interesting graphic that I've been kind of tracking. I think you'll find this interesting. So this is a worldwide map put together by Johns Hopkins. These little red dots are given relative to the size of the outbreak. So if I go over here to China, for instance, boom, look at that. It's a big old red dot right there. In all likelihood, that probably corresponds to Wuhan or something in the Hubei province. You can kind of see all the stuff that's going on. So there's 185,000 confirmed cases worldwide. And I'm not showing you this because I want to make you panic even more. But I found reason to kind of calm down a little bit when I look at these numbers. I think it's helpful. So for instance, if I zoom in right here, here we are in Ohio, 50 confirmed cases. You can click on the little bubbles and it'll tell you how many are there. One thing that's true that's kind of interesting, there's 967 cases in New York, okay? And let's see, where were some of the other big ones I found? Oh yeah, if you go over here to California, there's 557. And up here to Washington, 904. So if you go in this graphic right here, there are 4,661 cases total in the US. And I added those three numbers together just from those three states, Washington, California, and New York, where there seems to be a large number of cases. So it looks like there's something let me see here, 4,661, yeah, 2428 total cases coming from those three states alone. So more than half are from those three sectors. And the other graph that I think is interesting is this one. This is not part of the course, but you're number nerds as well, so I think you'll enjoy this. So this graphic is helpful, I think. It shows the total number of cases, tracking this data that came into us from China, from the World Health Organization and various entities that are tracking the epidemic or the pandemic, I guess is what it is now. So you see this thing's kind of leveled off. There was an inflection point back here where they started taking more extreme measures, and it went from kind of exponentially increasing to kind of logarithmically approaching this, or logistically approaching this this upper limit of around 81,000. Seems like, so this yellow curve is cases elsewhere in the world, and it seems like the measures we've taken, and this is helpful because this is from today. It looks like we may have reached a similar kind of inflection point in what's going on. And of course, the green curve is total recovered. So we've surpassed the number of Chinese cases around the world. And of course, the United States is included in that, included in the yellow chart in total. But I think there's reason to hope in that this curve has reached an inflection point. It looks like we may top out sooner rather than later. So that's helpful, especially with all the measures we've been taking. Over here, by the way, the death rates are sort of inflated because not everybody is actually tested that actually has the disease, right? So, I wouldn't freak out too much about that. And the other thing I wanted to point out is the following. So look at the US and Switzerland. So the US has 4661 cases that are confirmed so far. The US has 330 million people in it and a land mass of around 3.8 million square miles, whereas Switzerland has 2,330 cases, about half the number in US. Okay, so that's interesting. So, and they also have about 8.6 million people. So we have 38, I did a little computation, we have 38 times the population as Switzerland. We're on a similar timeline as Switzerland. And yet we only have double the number of cases, yet we have 38 times the number of people. Moreover, Switzerland is 16,000 square miles versus 3.8 million square miles, which is, we have about 246 times the land mass. So we have way fewer people per square mile, for instance. Okay, so I think that's reason to hope. We only have double the number of cases, yet we have, yet we have 38 times as many people, and those 38 times as many people spread over 246 times as much space in the physical United States. So that's interesting, I think. The other thing I would point out is Wuhan, or China topped out at around 81,000 cases. I think that's what it says. Yeah, like 81,000. And they have around 1.4 billion people. And that's about 4.25 times the population of the United States. Since they had 81,000 cases, if you just kind of do a rough calculation, 4.25 times as big, we've taken some pretty extreme measures trying to curb this thing. We have a very similar land mass to China, which is interesting. Then it seems like at worst we'll end up, in the 19 to 20,000 case range, as long as we're careful. So again, we have far less people per square mile. So I don't know. 19 to 20,000 seems like a pretty high upper estimate for confirmed cases, but who knows? Maybe all that'll be wrong. Anyways, I just thought I would point that out. Okay, so next thing I want to do is go into Desmos. But first I want to show you a computation I have on the board behind me with this Pareto distribution. Okay, so we'll go into Desmos here in a minute, but I want to show you this thing behind me. Okay, so here we go. All right, so here's the Pareto distribution up there. So f of x is equal to k theta to the k over x to the k plus 1 for x bigger than or equal to theta, and it's equal to 0 for x less than theta, right? That's what the density is. And I just went straight for the throat on this one. I decided to compute the cumulative distribution function. Okay, and so I just took a number b bigger than or equal to theta because I wanted to use x as the variable of integration here. So I didn't want to really put x in the limit here. Okay, so f of b that's the probability that x, that the random variable x with this distribution is equal to or less than b is going to be the integral from minus infinity to b of this density dx. Okay, and how does that get computed? Well, nothing happens, like from negative infinity up to theta, this density is 0, so that just goes away, and we just end up with the integral from theta to b. Okay, so b is equal to or greater than theta. And it's going to be k theta to the k over x to the k plus 1. Okay, that's what I'm integrating. X is my variable of integration. And what I can do is I can write this as x to the minus k minus 1. Okay, and then I can add 1 to the power, which gives me x to the minus k instead of x to the minus k minus 1. And I divide by negative k. And so the k's are going to cancel. You are going to have a minus sign. So you get negative theta to the k, x to the minus k, evaluated between theta and b. All right. And of course, you know, I could rewrite that as just negative the quantity theta over x raised to the k evaluated between theta and b. Okay, and finally, if I plug in b for x, that's going to be negative theta over b to the k, which is what this is. And if I plug in theta, it's going to be minus negative, which is plus 1 to the k. So I end up getting a cumulative distribution function. So this is f of b that equals that, and that kind of makes sense. Okay, and one thing you have to realize is, of course, this thing is 0 if b is smaller than theta, because the density was 0 for x smaller than theta. Okay, so really in the end, let me just kind of write this over here. Well, actually, I write it over here. Okay, write it over here. So what do I get? You know, the density, I'll write it in terms of x now, or the CDF f of x is equal to what? Well, it's equal to 1 minus theta over x to the k if x is equal to or greater than theta. Okay. And what is it if x is less than theta? Well, if x is less than theta, I haven't accumulated any probability yet, so that's just 0. Okay, so there is the CDF for this thing. So here's the CDF for that thing. Yeah. Okay, so that's nice. And what I wanted to show you was this Desmos graph. Okay, I did some work in here in Desmos. So let me just explain what I did here. I straight up it didn't like it when I was putting theta. So what I did is I said, okay, well, here's my density. Little f of x equals, okay, when x is equal to or greater than t, which I'm thinking of as theta, it's k t to the k over x to the 1 plus k. I was having trouble making the plus 1 stay in the power, so I had to mess with that for a minute. So there's that. So remember, t is like theta. And if x is less than theta, this thing is 0. Okay, so that is the orange looking curve. And if you put t and k in there, it'll give you the option to make these sliders. So here's these sliders, right? Here's what happens if I move t around. I get different things, right? And here's what happens if I move k around. Okay, and here's what happens if I do both. Okay, so T and K are going crazy, you know what I'm saying, right? Okay, there we go. That's pretty cool. Okay. Now that, you know, I want to be able to see this thing a little bit better, so let me pick one. Okay, so there we go. Okay, so there's T and there's K. Okay, there's T equal to 3.15 and K equal to 1.5. Now, one thing that I will point out is if you let, so I don't know if you can see in the little window behind me, I think you can. If you let x go to infinity on this, clearly the cumulative distribution function goes to 1 as x goes to infinity, as it should. Okay? And it goes to 0 if I go to the left, yes? Eventually it drops down to 0. Of course, if I plug in, look at this. If I plug in x equal to theta, I get 0. So the thing drops down to 0 at theta, and then it stays at 0 to the left of theta. Okay. So, and I kind of I put the graph of the CDF right here. So here it is right here. So for x equal to or greater than theta, it's 1 minus t theta over x to the k, and for x less than t, it's 0. Okay, so like if I put this in there, there it is, right? So there's the CDF sitting right there. That's pretty cool. And I see the CDF and the PDF right there on the same screen. Of course, you know that the CDF had to be continuous. It is. And if I take the derivative of this, of the cumulative distribution function, I will get this orange curve, okay? All right, I think that's all I have to say for now, but I just wanted to show you that Pareto distribution in toto, okay? So that's it for now.